Pre-calculus students, welcome to your 5.3 notes. Today we're going to take a look at solving trigonometric equations. We're going to use some of the skills we've learned early in this chapter and use them in a new way. I think you'll find that it'll have challenges, but at the same time, most of the stuff you'll see here today, you probably could have figured out without me telling you how to do it, at least at some level. So let's get started. Here we go. Number one says to solve tangent of x plus the square root of 3 equals 0. So what I'm going to do is actually start by just getting tangent of x by itself. And then I'm looking at the unit circle. And by the way, if you don't have a unit circle out, you should grab one. You can use your own, or you can grab one that's mine. It doesn't matter, but have one available because we're going to use it a lot. And so what I need to look at is, where is the tangent function equal to negative square root of 3? That happens in two places. One of those is 2 pi over 3, and the other place is 5 pi over 3. So we're talking about in quadrant 2 and in quadrant 4. And then what we can do is say, well, it's not just those places, but it's also any coterminal angles. So I'm going to add 2 pi in. Again, 2 pi would be the one full period. N means times any integer, so it would take care of all the, all the coterminal angles. Now, one thing you might think about with tangent is that our period is actually shorter than 2 pi. It's actually just pi. And if you think about the numbers we just found here, 2 pi over 3 and 5 pi over 3, they're actually separated by exactly pi radians. So the best answer for this question would be 2 pi over 3 plus pi n, because you can condense it just down to that one result. Okay, let's take a look at the next one. On number 2, we have an issue that we have sine function on one side of the equation and cosine on the other. So what we're going to do is change this sine function to be 1 minus cosine squared of x is equal to 3 cosine squared x. And then what I want to do is get all the cosines on the same side of the equation, like you see here. And then I can divide. So I know cosine squared x is going to be 1/4. Now the way to undo a cosine squared is to take the square root. So what I'm going to have here is cosine of x equals plus or minus 1/2. All right, so now we know what we're looking for is places where we see a cosine value of 1/2, and that actually happens at 4 different places around the unit circle. Those places would be pi over 3 would be the first one. Sorry, I was jumping ahead of myself there. Pi over 3, we'd also see that at 2 pi over 3. We would see it at 4 pi over 3, and also 5 pi over 3. And what you'd notice is that it's those 4 plus every coterminal angle to those 4. So the plus 2 pi n takes care of all the coterminals, whether it's part of the first trip around the unit circle or the 17th trip around the unit circle. By the way, one thing I should probably point out here, again, on this one, we could simplify and decrease, like get this down to 2 terms instead of 4, because pi over 3 and 4 pi over 3 are separated by pi. Same story with 2 pi over 3 and 5 pi over 3. I could change this just to be pi over 3 plus pi n and 2 pi over 3 plus pi n, and that would work. I'm not picky about that as long as you get the right values like I have here. But again, we've covered every single possible value. Okay, looking ahead at the next 2 questions, we have multiple angle situations. So when I say multiple angles, what I'm referencing is, like on number 3, we have a 3x, and on number 4, we have a 4x. And so we're going to look at those, and the way we treat those is a little different than what we've done with the other problems. So just pay attention to what we do here. Essentially, I'm going to ignore that this 3x even exists. As a matter of fact, if you wanted to, you could even do a substitution and lose the 3x. Like I could do something like u equals 3x and just rewrite this as tangent squared u equals 3. Well, then to get u by itself, we would first take the square root of both sides. And then we know that u is the inverse tangent of plus or minus square root of 3. And that happens at a couple of places. Pi over 3. And the other place would be 2 pi over 3. And in both cases, we would add pi n. Okay, so again, that's for the tangent function. And I know there are technically 4 places, but if you notice, I did plus pi n, so that's covering that. Now, I want to make one little adjustment. I said here that u equals 3x. I'm going to actually go back and just change this u down here and substitute it back in and say 3x equals, because in the end, what I'm looking for is not 3x, I'm looking for x. So what I'm going to do to finish this problem is just divide everything by 3. So x is going to be pi over 9 plus pi over 3n, and the other option would be 2 pi over 9 plus pi over 3n. So those are your solutions. Again, an infinite number of solutions, any quadrant in this case would be fine. Okay, number 4, we have a really similar situation. We're going to, again, use the multiple angle situation, but I want to actually not deal with secant if I can avoid it. You can. Some of you are smarter than me. You can do secant just fine. But for me, I'd rather just flip this and make it cosine of 4x equals 1/2. Because for me, finding where cosine is 1/2 is super easy. And cosine is equal to 1/2 in the first quadrant. That would be at pi over 3. Also, this would be true in the fourth quadrant at 5 pi over 3. And in both cases, we have to consider all the coterminals, which happen every 2 pi radians. At this point, we just solved for 4x, but remember, we're trying to solve for x, so I'm going to divide everything by 4. So I'm going to have pi divided by 3 divided by 4, which is pi over 12. And then instead of plus 2 pi n, it ends up being pi over 2 times n, or 1/2 pi n. You can write it different ways, but something like that. And then the other one would be 5 pi over 12. And we would still be adding pi over 2 n. So again, infinite number of solutions, those cover them all. As we move on, notice this time we have a restricted domain. So we're changing instructions on these. And these are important to kind of distinguish between the two types. So we were changing instructions. We're actually going to treat these problems the same initially, but we just have to answer a little bit differently at the end. Now here's the first thing I noticed about number 5 is we have a sine squared on the left, but we have a cosine of x on the right. We do not like to have different trig functions. So what I'm going to do is I'm going to change it so I actually only have cosines in this problem, because it's going to be a lot easier to factor or work with in other ways if I only have one trig function. So I'll go ahead and distribute this 2. And then I'm going to move everything to one side. And what you'll notice is the 2's will go away, and we'll have 2 cosine squared x plus the cosine of x. Now the fact that we have 2 cosines here and 1 cosine here tells me I can go ahead and just factor out a cosine of x, and I'll have 2 cosine of x plus 1. All right. Now, just like when we factored before, we can use the zero product property. If a times b equals 0, then a equals 0. Or b equals 0. All right, and this second equation is going to end up being cosine of x equals negative 1/2. So essentially what I can do in this problem, there's a couple ways to approach it right here. I could do the general solution that we've done on the previous 4, but honestly, when it's a pretty straightforward one, I think it's okay just to, look at the unit circle and say, hey, well, cosine of x is 0 at 2 places. That's pi over 2 and 3 pi over 2. And negative 1/2 also happens at 2 places. Those places would be 2 pi over 3 and 4 pi over 3. And we have exactly 4 solutions. Now we're going to run into a little bit different scenario on some of the others when we do that, particularly if we have multiple angles. This gets a little trickier, but for that, that's pretty straightforward. All right, let's look at number 6. Now this one, we don't have to do a lot of setup work, but you have to recognize that we can actually factor this. So I'm going to rewrite this as 2 sine of x plus 1 and sine of x plus 1 equal to 0. Again, the zero product property, and I'm going to move through this fairly quickly, but we know sine of x is equal to 1/2, negative 1/2 I should say, or the sine of x is equal to -1. We can just solve either of those. Now, again, we could do the general solution, but I would suggest that it's probably easier just to look at the unit circle and write down the 3 places. So sine of x is -1/2 at 7 pi over 6 in quadrant 3. In quadrant 4, we get 11 pi over 6. The sine of x is -1. That only happens at one place. That's 3 pi over 2. We have 3 solutions to that equation. Exactly 3. All right, we're moving on to our last 2 problems. It probably won't surprise you to hear that often the last few questions tend to have extra challenges. These are no exception. I especially think that's the case probably on number 7. So pay attention here. Now, we have a secant and a tangent. Now, we have a Pythagorean relationship that works really well with those. Unfortunately, this is not secant squared and tangent squared. This is just secant and tangent. So I can't change the secant to a tangent. I can change a secant squared to a tangent squared though. So here's what I'm going to do. I'm actually going to move the tangent to the other side. And you say, well, what's that accomplish? Well, what this allows me to do is actually to square both sides of the equation. So I'm going to do that. And I'll have secant squared x is equal to, and then I'm going to go ahead and FOIL this thing out. 1 minus 2 tangent of x plus tangent squared x. And again, like, okay, well, what did we accomplish? Well, what we accomplished was now we have secant squared, which we can change to 1 plus tangent squared. Those Pythagorean identities, really helpful if you know them well, especially. Okay? And then we're looking at an equation that only has tangents on either side, and those tangent squareds are going to cancel each other out. Actually, the 1s are going to cancel each other out too. So all we're left with is -2 tangent of x is equal to 0, or you could just simply think of it as just tangent of x equals 0. And then we just look at where that happens, and that happens only at one place, well, 2 places in the unit circle, but they're separated by exactly pi radians, because it happens at 0, it happens at pi. I guess you could argue 2 pi is there too, but I'm just going to write it as pi n. Okay, 0 radians, pi radians, 2 pi radians, and so on. And that's all solutions. Every time this is true, then x has to be a multiple of pi. All right, we found the problem we were looking for, the last one. All right, this one again has some more complications, but you'll notice we already have a secant squared. I'm going to use that to my advantage and go ahead and change this to 1 plus tangent squared. Now remember, the angle here is actually a double angle, so it's 1 plus tangent squared of 2x plus the tangent of 2x minus 3 equals 0. All right, so let's start cleaning up our mess here. We're going to have tangent squared of 2x. I know it may bother you that we have a double angle going on here, but it's just something we're going to work through. We're going to treat the double angle just as any other angle until the end, and then we have to do some division to figure this whole shebang out. Okay, all right, so now this is actually a factorable quadratic. This is tangent of x plus 2 times the tangent of x minus 1. That would give us the correct middle term, so that's equal to 0. and I get two possibilities here. I could have tangent of x equal to -2 or tangent of x. And I made a mistake. I'm going to go back and fix that. I don't know if you guys caught that, but I left my 2 out of the angles. These are all 2x's, not x's. It happens to the best of us. It happens to me too sometimes. All right, so let's try that again. Tangent of 2x is -2, or tangent of 2x is equal to 1. All right, so this gives us some values. I'm going to start with the second one actually, because we know that the tangent function is equal to 1. That happens at pi over 4 and every pi radians after that. So you might also see like at 5 pi over 4, this would also be true. So it's pretty easy to find the values there. Now I know, well, this says to find all solutions, so we're finding general solutions here. So to finish the job, I'm going to divide by 2, and I'm going to have pi over 8 plus pi over 2 n. That's the easy one. The one that's sort of annoying is this other one, and it's annoying because 2x, or sorry, -2 I should say, is not a unit circle value. So we can't do what we've done before, which is just look at the unit circle, pick your angle 2, 3, 4, and roll with it. Instead, what we have to do is think of it this way. 2x is equal to the arctangent of -2. This becomes a calculator problem, unfortunately. Although you could perhaps argue you could do exact values with this as well. And in order to get all the coterminal angles, I'm going to add a pi in there. Okay, so I've kind of ran out of space, but squeezed it in there. I think you can see what's going on. There are a couple ways you can answer this. I'm going to use approximate values by punching in the arctangent in -2, and I got -1.107, and it's still going to be plus pi n. And then finally, we'd have to divide everything by 2, divide by 2, divide by 2, and I'm going to write my other answer right over here since I have some space. It's -0.554 plus pi over 2 n, which is sort of a weird answer because it's like an exact value of pi over 2n and then an approximation with it. But that's just the way it works. If you want to do exact all the way around, we could do something like the arctangent of -2 divided by 2 plus pi over 2n. I'm not sure if that makes any of you feel any better. Those will be a little challenging to make sure you answer them in the right format, but I believe in you. You can make it happen. Hey folks, I hope this lesson has worked for you. I think if you've done a good job of learning what we've learned in 5.1 and 5.2, that this will be kind of a smooth transition, just with a couple of little challenges here and there. But I think it's a great little section. Hope you guys have learned something from this, and we will see you soon.